we have the first question with the 7 marks. Apply the concept of partial differentiation to prove this partial differential equation, second order partial differential equation, when the relation consists two arbitrary functions where x and y are independent variables. Z is the dependent variable. We need to eliminate the arbitrary functions f and g from the relation. First, you need to differentiate the relation partially with respect to x. We got this. Again, differentiate partially with respect to x. You got this relation where z is given relation. Differentiate z partially with respect to y. We got this. Later, you need to differentiate the relation with respect to y one more time. You got this. From these two second order partial derivatives, one can observe that dou square z by dou y square is a square times dou square z by dou x square, which is the required partial differential equation.
By eliminating arbitrary functions from the given relation, now you can see
it is the second question with the 3 marks weight. Examine the functional dependence among two functionals u and v where x and y are independent variables. U and v are functionals. You need to find the first order partial derivatives to u with respect to x and y, partial derivatives of v with respect to x and y. To check whether the functional dependency, you need to consider Jacobian of uv with respect to xy, that is determinant with the 4 entries, dou u by dou x, dou u by dou y presented in the first row, and similarly the second row entries are from the second functional. The determinant gives 2, which is non-zero. We came to conclude that functionals u and v are not functionally dependent. That means those are independent. You have a second question from unit number 1. Find the Taylor series expansion of e power x cos y about the point 1 pi by 4. So this is a 7 marks question. We are given that the function according to Taylor series about the point AB, f of AB plus x minus a into dou f by dou x at the point AB plus and so on. You have the second order partial derivatives at the point AB. This is called Taylor series expansion about the point AB for fxy. You need to find f of 1 comma pi by 4 dou f by dou x at the point 1 comma pi by 4, dou f by dou y at 1 comma pi by 4, dou square f by dou x square at the point 1 comma pi by 4, and similarly you have a second order partial derivatives at the point 1 comma pi by 4. Substitute these values in the above Taylor series expansion about the point 1 comma pi by 4. We have obtained this right hand side expansion as a Taylor series for given function e power x cos y about the point 1 comma pi by 4. This is for 7 marks. Now you can see 3 marks from unit 1 as a second question b bit. Determine the functional relationship between u, v and w. Given that functionals u, v and z. Once you can observe that v and w are second degree expressions, u is a first degree expression, so that you consider u square to make a second degree expression. Basically u is x plus y plus z, and after squaring you got this expression where x square plus y square plus z square is v, and xy plus yz plus zx is w. Hence we have obtained the functional relationship among u, v, w is u square equals to v plus 2w. Now you can see unit number 2. Find the values of the double integral. Here we have integral 0 to 1, integral 0 to square root 1 plus x square. One of the limits in terms of x. So these limits belongs to y and the constant limits are for x. So integrate partially with respect to y while x can be treated as a constant. Here we have made square root 1 plus x square as p. We have integral 0 to 1, integral 0 to p 1 by p square plus y square dy dx. We know that integral 1 by p square plus y square is 1 by p into tan inverse y by p whose limits from 0 to p. On simplification, we have obtained that integral 0 to 1, 1 by p, tan inverse p by p is tan inverse 1, that is pi by 4 minus 0 dx is only pi by 4 constant. P already we have made mentioned that square root 1 plus x square dx. So pi by 4, we know that log of 1 plus square root x square plus 1 is the integration to 1 by root over 1 plus x square with respect to x. On substitution, the upper value log of 1 plus root 2 minus lower value log of 1 plus 0, log 1 is 0, we have obtained pi by 4 times log of 1 plus root 2 is the required value of the double integral.
Evaluate the double integral over the upper semicircle x square plus y square equals to a square. It is the double integral in the polar coordinate system where r and theta are polar coordinates. The reason is upper semicircle r vary from 0 to a. The upper semicircle lies in the first and second quadrants of the xy plane. Therefore, the limits of theta from 0 to pi. All limits are constants. R square integration with respect to r power 3 by 3. Consider the limits between 0 and a. We have a power 3 by 3 and the resultant integral 0 to pi sin theta d theta. Sin theta integration minus cos theta. Substitute the limits of theta from 0 to pi. You get cos 0 minus of cos pi. 1 plus 1 is 2. 2 into a power 3 by 3. 2 by 3 a cube is the required result. It is 4a 7 marks question. Make use of triple integral to find the volume of the tetrahedron bounded by the planes. Here x is equal to 0, y is equal to 0, z equal to 0 are coordinate planes, and you have x by a plus y by b plus z by c is 1. My target is to find the volume of the tetrahedron. To get the required volume, we need to find the limits of x, y, z. The lower limits of x, y, z are 0 from the coordinate planes. We have to find the upper limits of x, y, z respectively. Now you can make z as a subject from the relation x by a plus y by b plus z by c is 1 is c times 1 minus x by a minus y by b. To get the upper value of y, we have the relation x by a plus y by b is 1. Y is b times of 1 minus x by a as upper result for y. We have the relation x by a is equals to 1 for getting upper limit of x. Required volume triple integral dz dy dx. Since integral over v dv is the required volume, substitute the limits of z by x. The inner integral is with respect to z. integral 1 dz. After substitution of limits, the integrand will be c times 1 minus x by a minus y by b. Integrate with respect to y and substitute the limits. The integrand is in terms of x. Again integrate with respect to x. We get the result as a by abc by 6. Now you can see fourth B 3 marks question. Evaluate the double integral xy dx dy over the positive quadrant of the circle x square plus y square equals to a square. This is one of the problem which requires the transformation. For simple evaluation, the positive quadrant means first quadrant. So here we have the transformation. X is r cos theta, y is r sin theta, dx dy is r dr d theta. X is equals to r cos theta, y is equal to r sin theta, xy becomes r square cos theta sin theta, and in dx dy you have r overall r power 3 cos theta sin theta integrand, and the limits of are 0 to a and theta limits from 0 to pi by 2, since the region lies in the first quadrant, that is a positive quadrant. R power 3 integration with respect to r power 4 by 4. By substitution of limits you have a power 4 by 4. Cos theta sin theta is sin 2 theta by 2. So a power 4 by 4 into 2 is a power 4 by 8 sin 2 theta integration minus cos 2 theta by 2, that gives us a power 4 by 8 as the required value of the double integral over the positive quadrant of the circle. Now you can see unit 3, find the angle of intersection of the spheres at the point 4 minus 3 2. So first we need to find the gradient of f, that is del f, del I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z. F is x square plus y square plus z square minus 29. We get del f 2xi bar plus 2yj bar plus 2zk bar. Del f at the point which is the required vector. Del z, that is a gradient of second scalar, where g is x square plus y square plus z square plus 4x minus 6y minus 8z minus 47, where del is vector differential operator I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z. On operation you get del z as this one. Del z at the point P is 12y bar minus 12j bar minus 4k bar. We know that the angle between two surfaces is cos theta is equals to del f at the point dot del z at the point whole by modulus of del f at the point P into modulus of del z at the point P. On simple calculation, cos theta is equals to 152 by this denominator numerical value. Hence theta is equals to cos inverse 152 by this numerical value. 3 marks question. Examine whether the maximum directional derivative of the scalar point function at the point P is square root 165, where P 1 minus 2 minus 1. We need to find the gradient of scalar point function phi del phi, where del I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z, it gives this vector. Del f at the point P is this vector. Maximum directional derivative is modulus of gradient of phi at the point. It gives square root 165. Make use of the concept of curl of a vector to find the constants ABC if f bar is irrotational. We need to find constants ABC when we have three equations in terms of ABC. Here f bar is irrotational. First we consider the curl f bar del cross f bar. It is the determinant with 9 elements. In the first row we have to write unit vectors I bar, j bar, k bar. In the second row we have to write dou by dou x, dou by dou y and dou by dou z. Third row elements are the coefficients of I bar, j bar, k bar, and we know that f bar is irrotational. Curl f bar is equals to 0 bar, del cross f bar equal to 0 bar. So by first row expansion to the determinant, on simplification we have obtained that the left hand side vector in terms of ABC, 0 bar is the 0 vector. By comparison we have c minus 3 is equal to 0 means c is equals to 3, 2 minus a is equals to 0, a is equals to 2, b minus 3 is equal to 0, b is equal to 3. These are the constant values by using the concept of irrotational. So determine whether the vector f bar is solenoidal. Now you can find divergence of f bar, that is del dot f bar, where del is vector differential operator I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z. By dot product you have this result. On simplification, divergence of f bar is y square plus x square z minus 2yz. Here the partial derivative of x means yz can be treated as a constant. Simply we remember that when we have to get the partial differentiation to the function with respect to one variable, rest of the variables can be treated as a constants. At that point 1 1 1 you get 0. Divergence of f bar at the point 1 1 1 is 0 means given vector is a solenoidal vector. Coming to unit number 4, find integral over c m dx plus n dy, where c is a closed curve which is bounded by the curves y is equals to x and y equals to x square using Green's theorem. First you need to draw the rough sketch of the region. Y is equals to x is a straight line which is passes through the origin. Even powers of x is symmetric about y axis, that is a curve which is symmetry with respect to y axis. Now you can see statement of Green's theorem, integral over c, where c is a closed curve, m dx plus n dy is equals to the double integral over the region dou n by dou x minus dou m by dou y dx dy, where m and n are continuous functions whose first order partial derivatives exist. Consider dou m by dou y 5x, dou n by dou x is 4, where m is equals to 5xy minus 6x square, n is coefficient of dy, that is 2y plus 4x. Based on the functions m and n, we have obtained these partial derivatives. Now you can see from the region we have drawn a vertical strip on the region to get the limits of y. The lower curve is x square, so that the lower limit for y is x square and the upper curve is x here. So you have the upper limit for y is x and x limits from 0 to 1. Why? Because the region which covers from the value of x 0 to 1 and double integral over r dou n by dou x minus dou m by dou y dx dy is integral 0 to 1 integral x square to x for y. 4 minus 5x is that integrand dy dx. One of the limits in terms of x, first integrate with respect to y and then integrate with respect to x. It gives us 1 by 4 by the concept of Green's theorem. Now you can see, examine whether this minus 1 by 6 where c is a curve in the xy plane moving from the point 0 0 to 1 2. Here we have the curve y is equals to 2x square, which implies that dy is equals to 4x dx, and based on the points we have x limits from 0 to 1, x lies between 0 and 1. Consider f bar dot dr bar. F bar is 3xy I bar minus y squared z bar. Dr bar is dxi bar plus dy z bar. Now you can see here the resultant integrand f bar dot dr bar based on y is equals to 2x square. You have 6x cube minus 16x square dx, and you consider integral over c f bar dot dr bar. That means x lies between 0 and 1. F bar dot dr bar gives integral 0 to 1 6x cube minus 16x power 5 dx. After substitution of the limits for x from 0 to 1, we have minus 7 by 6 as the result. Now you can see, find the surface integral over s f bar dot n bar ds using Gauss divergence theorem, where f bar is this vector point function which is taken over the surface of the cube bounded by the planes x is equal to y is equals to z equals to a and the coordinate planes. First we have to apply Gauss divergence theorem. We know that the integral over s f bar dot n bar ds is the volume integral over v del dot f bar. Del dot f bar means divergence of f bar. So del dot f bar means del I bar dou by dou x plus j bar dou by dou y plus k bar dou z. F bar is this vector point function. After applying a vector differential operator on vector point function, you get x square plus 1, and by Gauss divergence theorem you have this result. So integral over s f bar dot n bar ds is equal to integral over v del dot f bar dv, that is integral 0 to a integral 0 to a integral 0 to a divergence of f bar x square plus 1 dz dy dx. So all limits are constant limits. We have integrate with respect to x, you have x square integration x power 3 by 3 plus 1 integration with respect to x is x a cube by 3 plus a, and the rest of the part integral dz is a, integral dy is a. So a square into a cube by 3 plus a is a power 5 by 3 plus a cube. Now you can see 8th B 3 marks question. Examine whether integral over s f bar dot n bar ds is 4 pi 3 a plus b plus c, where s is the surface of the sphere, by using Gauss divergence theorem. Here f bar is axi bar plus byz bar plus czk bar. As per the Gauss divergence theorem, first we need to find del dot f bar, that is divergence of f bar, where del I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z, which is operate on the function f bar, which gives a plus b plus c. So integral over s f bar dot n bar ds is integral over v divergence of f bar dv. So substitute divergence of f bar here, a plus b plus c is constant, integral over v dv. So integral over v dv is only 1 v, where v is the volume of the sphere, that is 4/3 pi r cube, where r is 1. You have 4 pi by 3 1 cube into a plus b plus c. Hence the required result is 4 pi by 3 a plus b plus c. Next you can see unit number 5. Find the general solution to the partial differential equation. It is 4d square plus 12d d dash plus 9 d dash square of z equals to e power 3x minus 2y. The right hand side function is in the form of e power ax plus by. The general solution is complementary function plus particular integral. First we need to find complementary function, write auxiliary equation. D is replaced with m and d dash replaced with 1 and equating it to 0. That operator form becomes 4m square plus 12m plus 9 is equal to 0 as auxiliary equation. It is a quadratic equation. It has 3 roots and repeated roots minus 3 by 2, and the complementary function in terms of arbitrary function. The general solution always in the form of z equals to phi of y plus mx. It is repeated so that we have phi 1 of y minus 3 by 2x, where m is minus 3 by 2 plus x into phi 2 of y minus 3 by 2x. Once you remember that, it is always in the form of phi of y plus mx. So m is repeated, you can write first one is 1 into phi 1 of y plus mx plus x into phi 2 of y plus mx. In case of it is repeated thrice, you can write plus x square phi 3 of y plus mx. Particular integral will be 1 by 4d square plus 12d d dash plus 9d dash square of e power 3x minus 2y. Whenever you have d, that d replaced with the coefficient of x3 and d dash is replaced with the coefficient of y minus 2. But here when d replaced with 3 and d dash replaced with minus 2, the denominator becomes 0, and multiply with x and differentiate the denominator with respect to d partially, and again you get 0 by replacing d with 3 and d dash with minus 2, and again multiply with x and differentiate partially with respect to d, and you have x square by 8 into e power 3x minus 2y is the particular integral. Hence the required general solution, the complementary function plus particular integral. It is 9th B question, 3 marks. Examine whether PD capital P small p plus capital Q small q is equal to capital R is the partial differential equation which is obtained from the relation z equals to f of sin x minus cos y by eliminating arbitrary function f. It is a relation. That relation is consists on arbitrary function, so that we get the first order partial differential equation. So as we know, one arbitrary function presented in the relation, by elimination of such arbitrary function we will get the first order PDE. So here it is the relation, let it be 1, differentiate the 1 partially with respect to x, you get this relation, differentiate the equation 1 partially with respect to y, we get this relation, and left hand side we have the same expressions, the right hand side expressions are equal. On simplification, we have obtained this first order PDE. It is a 10th question a bit, 7 marks. Apply the procedure to solve this partial differential equation. It is a Lagrange's linear PDE. You can write auxiliary equation dx by capital P is equal to dy by capital Q is equal to dz by capital R. You remember that the Lagrange's linear PDE is always kept in the form of capital P small p plus capital Q small q is equal to capital R. So auxiliary equation dx by capital P is equal to dy by capital Q is equal to dz by capital R. Now consider the first two ratios. So by eliminating third variable, we are grouping these two ratios. You get a x square plus y square is equal to c1 by variable separable. It is u equal to c1. First we need to find two independent solutions to the system of equations. When we are grouping first two members, you get this independent solution to the auxiliary equation. The next one is we consider second and third ratios. Dy by minus x is equal to dz by minus x into e power. Already we have seen that the relation x square plus y square is c1. Utilize it on simplification. So we have eliminated the first variable x here, minus x cancelled. You have dy is equal to dz by e power c1. The third variable completely eliminated. So you have a variable separable. You have z minus y times e power c1 is equal to c2, where c1 is x square plus y square. So this is the second independent solution to the auxiliary equation. So the general solution will be phi of uv is equal to 0, where u x square plus y square, v z minus y times e power x square plus y square, which is the required general solution to the Lagrange's linear PDE. Now you can see the 3 marks question. Determine whether this partial differential equation obtained from the relation where a and b are two arbitrary constants. To eliminate two arbitrary constants from the given relation, once we remember that the number of independent variables equals to the number of arbitrary constants, one can obtain a first order partial differential equation. So already here we have made mention that PQ is 4xyz as a partial differential equation. By elimination of arbitrary constants here, we have the relation, let it be 1, and differentiate 1 partially with respect to x. You get this, differentiate 1 partially with respect to y, we get this relation. On elimination, multiply with these two, p into q is equal to 4xy x square plus a into y square plus b. Already we know that x square plus a into y square plus b is z from given relation. Thus we have obtained pq as 4xyz, which is a first order partial differential equation. Now you can see the scenario based question, direct 10 marks question from unit number 3, vector differentiation. Let the temperature at any point in the space is given by the temperature function in terms of xyz. It is a algebraic function in terms of xyz. It is a cubic expression. Estimate the direction in which the temperature changes most rapidly with the distance from the point P, and the maximum rate of change of the temperature in that field from the point P. The directional derivative of the temperature at the point P in the direction of some non-zero vector. And finally, we need to estimate unit normal vector to the temperature function at the point 1, 2, 3. So basically the temperature function is already made mentioned here. So the direction in which the temperature changes most rapidly with the distance from that point means you need to find gradient of the temperature function at the point P. So gradient of the temperature function is del T at the point P. So del is I bar dou by dou x plus j bar dou by dou y plus k bar dou by dou z, where T is xy square plus yz square plus zx square. So the vector differential operator is operated on that temperature function, which gives us this vector point function in terms of x, y, z. Del t at the point P, wherever you have x replaced with 1, y replaced with minus 1, z replaced with 1, you got this vector. The second point is the maximum rate of change of the temperature in that field from the point means maximum value of the directional derivative. So already you have del t at the point. Take a magnitude to that vector, and you know that ai bar plus bj bar plus ck bar is square root a square plus b square plus c square. As per the formula, we have obtained square root 3 square plus minus 1 square plus minus 1 square. The result will be root 11. Third question, the directional derivative of the temperature function at the point in the direction of some non-zero vector. So first you need to find the unit vector. So E cap is the unit normal vector to the vector I bar minus 2j bar plus 2k bar, whose length square root 1 square plus minus 2 whole square plus 2 square is root 9 is 3. So the unit vector become I bar minus 2j bar plus 2k bar by 3. The directional derivative will be, so delta at the point P dot this E bar. Already we have del t at the point P is 3I bar minus j bar minus k bar. So unit vector will be I bar minus 2j bar plus 2k bar by 3. On simplification, the dot product of two vectors gives again scalar, that is 3 by 3 is 1, which is the required result of directional derivative to the scalar point function, that is a temperature function at the point 1 minus 1 1 in the direction of some non-zero vector. The fourth one is the unit normal vector to that temperature function at 1 2 3. Del t already we have found from the point 1 in terms of xyz, but here the point is 1 2 3. Wherever you have x replaced with 1, y replaced with 2, z replaced with 3, you get this non-zero vector. And unit normal vector means this vector can be divisible by its own length. The length will be square root 10 square plus 13 square plus 13 square, 10 square 100, 13 square 169, and 13 square 169. Overall it is 438. Hence the required unit normal vector to the temperature function at the point P is this vector. So you can proceed as per the model paper, you will get more marks.